Okay, folks, that took all of about 6 seconds to figure out where that small error was. It was the very first one. When I took 2.5 and redivided it by 12, I didn't get 0.1875. I don't know what I did to get that. I screwed putting something up in the calculator. But it comes out being 0.2, not 0.1875. It's a small change because that hydrogen gets squared. It kind of multiplied or increased the magnitude of that small error and made it come out to be so we got 1.3 as opposed to 1.1. If you go back and put that in here, you will get 1.1 times 10 to the 7th. But it doesn't really matter. The point is it's a huge number. And that K value being huge like that, that's what you care about. Once you get to the magnitude of 10 to the 7th, whether it's 1.1 or 1.3, it's irrelevant. It is a freaking huge K value. That's a big number, which means that reaction really wanted to go and form that hydrogen sulfide. Okay. So I took the liberty of putting down the next equation we're going to need. You're going to need, this is loaded into essential documents. These are our equations. Okay, here are our equations for the second third, okay, our second unit. So go grab that. And, well, at one point you're going to want to grab that. It just has everything nice and convenient for you. All right, so let's take a look at the next problem. Problem 3. We're cranking along doing these problems. This is problem 3. This equation allows us to calculate a Kp from a Kc or a Kc from a Kp. That's what it allows us to shift gears. So if we have gases, then we can figure out what the Kc is. And like in the last problem, that's what we did, right? We figured out the Kc. If we wanted to, we can actually go back and figure out the Kp, what the Kp would be for that reaction. The Kp is going to have a different value to it because concentrations and are not pressures, but they have a relationship between them. And here's the interesting thing. I think it's interesting. All chemistry is interesting, but this is kind of neat. Look at the equation, 0.0821. Sound familiar? I hope so. It's a gas law constant. That was the atmospheric gas law constant. Because when you have gases, dealing with pressures, this is how we shift to Kp, is we've got to use something when the concentrations to get it back into a gas K. And that's where we use this constant. It's a derived equation. You don't have to worry about where it comes from. You just know how to use it. This is temperature in Kelvin. Kelvin, always Kelvin. And this delta N up here is going to be the number of moles of gas product minus the number of moles of gas reactant. In other words, how many moles of the stuff on the right subtract how many moles of the stuff on the left, and that gives you that exponent we're going to put up there. Okay, let's take a look at the problem. Problem 3. All right, so problem 3. So calcium carbonate, which is solid. Calcium carbonate, you know what it is. It's chalk, okay, that you write on the board back in my day. Yeah, you gotta clap together the things and all the dust was, and you like just, you're all dried out. Or the cliffs of Dover, calcium carbonate. Like the cliffs of Dover, I think, are limestone, which is calcium carbonate. So calcium carbonate. Babbling. I'll get back to it. So calcium carbonate, you know what it is, chalk. And this is going back and forth, and it's releasing some calcium oxide, and it's going to release also some carbon dioxide. Now the carbon dioxide is in a gas, calcium carbonate is a solid. It better be a solid. Yeah, it is. It's a solid. All right. I hope a little bell's going off in your head. We're not going to use those in an equilibrium expression. Okay. All right. We given anything else in this problem? Let's actually see what the problem's asking. At 800 degrees Celsius, the pressure of CO2, they gave me a pressure, is 0.236 atmospheres. So I have a pressure. If I'm given a pressure, not a concentration, which one is the easier one to do, the Kc or the Kp for pressure? Kp. So let's take a look at our Kp. What would our Kp expression be for this reaction? And I'm going with P for pressure because I was given a pressure. Well, remember, products over reactants, but we do not include solids. You don't include those ever, because you can't have a pressure of a solid. Hey, I got some carbon graphite over there. What's the pressure of that graphite? Doesn't make sense. So we're only going to put this in my expression. Carbon dioxide. This is a balanced reaction. So there are no coefficients, no exponents. So the pressure of the CO2 goes right there. That's my Kp expression. Nice and easy. Oh, crikey. Okay, that's my Scottish accent. Crikey. Australia. So I know what the Kp is if I just put the pressure right here of the CO2. Easy peasy lemon squeezy. Kp is equal to the pressure of the CO2, which I was given as 0.236 atmospheres. 0.236. You don't write the word atmospheres. K values don't have any numbers or any units associated with them. You just have the number. So that is my Kp. All right. All right. And it wanted us to find both, I believe. Calculate the Kc and the Kp for the reaction at this temperature. And we've got that one right. The answer is 0.236. All right. Easy. That was easy. Okay, now we have to do the Kc. And this equation here is the gear changing equation. So this equation allows me, if I have one of them, I can shift and get the other one if I prefer to have that concentration K value, which is what I want to find here. I have the Kp, so I'm going to put that here. So I'm going to go ahead and erase this. Yeah, I'll erase this. And Kp is 0.236 equals Kc. What we're trying to figure out, multiplied by 0.0821 times temperature in Kelvin, which is Italian for Kelvin. Remember, we had 273, so we have 800 plus 273, so that's 1,073. Okay, N. I need the number of moles of gas on the right, products. This is the only gas I have. How many moles of it do I have? The coefficients tell you how many moles you have. 1. I have 1 mole of gas on the right. How many moles of gas on the left? That's not a gas, so if this were a gas, if that were a G and I had one of those, I would say I have 2 moles on the right and none on the left, and I put a 2 here. Okay, just giving you another example, but that's not what we have. We have 1 mole here, it's not gas, and that's not gas. So 1 minus 0, anybody got a calculator? Billy, 1? Thank you. So I'm going to put a 1 up here, which essentially doesn't do anything. In other words, it doesn't do anything. If it was squared, that would certainly change things, but putting the 1 there just means whatever you have in here, that's what you got. Okay, so the 1 doesn't change anything. So I'm going to go ahead now and do the math. I need to multiply those two out and get a value. So let's multiply our 1,073 times 0.0821, and we get 88.1. So 0.236 equals Kc times 88.1. Solving for Kc, we'll divide both sides by 88. Okay, so 0.236 divided by 88.1. You should be checking me at home. Sometimes I hit the wrong things. I'm just trying to move this. I'm not trying to bore you like I'm boring you right now by talking to you. So check, okay? Check. I make mistakes sometimes. I just go too fast. So what do we get? 0.00267. All right, so let's round that to 0.0027. 268, I guess. 0.0, we'll have 3 significant digits. 0.00268. That's the same thing as 2.68 times 10 to the negative third. Okay, that's the Kc value. And let's just check and make sure we got it. Oh, nice. Crikey. We did it. We got the answer. See how good you and we are? See how we and you are? What does it mean? What does it mean? I'm going to keep coming back to this. What does it mean? What does this mean? That's a small number. It's less than 1. that means the reactants are favored. That means that this thing does not want to go in the direction that it's written. It does not want to break down. If you think about it, you know that's true. Take a piece of chalk. Okay? Imagination, piece of chalk. Or look at the cliffs of Dover. Maybe some of you have seen them before in England, south shore of England, facing Pas-de-Calais of France. Okay, you can see them apparently. You come back next year, are they going to be gone? Take a piece of chalk, lay it down on the desk. Come back next year. Still there. Of course it is. It's going to be there for a long time. Why? Because it doesn't want to break down. It doesn't want to do this. The calcium carbonate is stable. It doesn't want to break down into calcium oxide and carbon dioxide. I guess it will over a long period of time. If you came back, a million years from now, your little chalk is probably all gone. But it doesn't want to break down. It's a very slow process for this, which is indicated by this small K value. K values tell us the direction that the reaction wants to go. Okay? It does not want to go this way. These want to go that way. And if we reverse the reaction, if we took these, threw them over here and stick that over there, and then calculate a K value, we'll get a big number for these wanting to form that, okay? I will keep coming back to that. I will repeat, what does it mean? That means that doesn't want to break down. It wants to stay as it is. Okay. All right, a little chemistry there for you. Problem solved.